From the University of Leeds, and he's going to tell us about colouring random graphs randomly.
Thank you, Bill. And thank you to the organisers and the other Uber organisers for inviting me. So, well, the title kind of speaks for itself. So most of what I'll say to start with, you've heard many times before, but that's not going to stop me saying it. So I'll deal with a graph, but I'll speak about pairs, just any two vertices from a set V, which will be the integers 1 up to n for convenience. And so a graph has an edge set which is some subset of this set of pairs V2, which will be all the pairs. And the reason for that is that we can then choose these things at random. So the set of all graphs, I doubt that I'll use the notation, but it will be Gn, and Gnp will be the sort of Erdos-Renyi random graph. So for all pairs, we choose randomly with probability p independently whether that is an edge of G. And so this p is the density of the edges. And we'll also talk about the maximum degree of a graph, so that will be delta, or D as Eric calls delta. And C will be some set of colours, 1 up to Q. And a proper Q colouring, well, we've all seen that many times before, just means that the ends of any edge are coloured differently. So counting graph colourings is hard. It's hard for almost all values of Q and delta. Certainly if Q's at least 3 and delta's at least 3. For the remaining cases in P, the sharpest result is due to Catherine, I think. But
and you maybe.
Sorry?
And you.
I think you left me off the author list.
Yeah.
So approximately counting, on the other hand, or this sampling, as we've heard, is the same thing, doesn't have any kind of dichotomy result, as Eric told us. And most work is trying to bound the number of colours that you require to put sampling in P as a function of the maximum degree. Again, this is what we heard from Eric. And certainly the conjecture that Q's at least 1 plus epsilon delta has been made. Eric made an even stronger conjecture that Q at least delta plus 2 would do. But this has not been proved for other than very special classes of graphs. And the approaches to bounding this Q of delta are almost entirely based on Markov chain analysis. And the techniques, as we've heard, are usually coupling or path coupling. So the chain that I'm going to look at is the same one that Eric looked at, where you start with some colouring, any colouring you like, and you choose successively a vertex and a colour uniformly at random. And I'll use this notation AU of xt to be the number of colours which are available for you, that is, which don't appear on any neighbour of U in the colouring xt. So we look to see whether the colour we've chosen, this colour C, is in this set. If it isn't, well, if it is, it's in the available, it's not in the neighbourhood, then we recolour, otherwise we do nothing, and we keep doing this. So there is a a slightly different chain which people sometimes consider, where you choose randomly from this set. It's usually called the heat bath version. They seem to have similar properties. So just as a trivial example, here's a colouring. We choose a vertex uniformly at random, the one in the middle. We choose a colour. There's 6 colours. Suppose it's the blue. And we can recolour because when we look at these neighbours, there's no blue. So that would be the new colouring. But if we'd chosen green, say, we wouldn't have done anything because that one was already coloured green, and we would not end up with a proper colouring. So, well, I put this in for form's sake, but we've seen so many things like it that I won't spend very long. So we will view this as a Markov chain, and we'll measure convergence in total variation distance, and we'll be considering couplings, and the proof of convergence then goes via the coupling lemma, which I seem to have placed 5 years later than Magnus. I don't know which of this is right, but perhaps neither. So if the coupling can be made so that xt and yt, the 2 copies that are involved in the coupling, become the same very quickly, then the chain will converge quickly. So Mark Jerome first analysed that chain, and he used a coupling which I will now describe. It's not the one that Eric described, because he did it via path coupling. So this is slightly more complicated, but for reasons I'll eventually explain, is the way we choose to do it. So we'll suppose that the 2 chains choose a vertex and a colour. So x chooses ux cx and y chooses uy cy. So the coupling is that both of them choose the same vertex to recolour, and then they look at the colour sets that are available to them, which we'll call AX and AY, and those have sizes straight AX and straight AY. Then we map the colours to themselves in a slightly clever way. So if a colour is in both of them, so it's available to both of them, then it will map to itself. So we would always choose that. But then if the colours, say, available to X are smaller than those available to Y, we make sure that we map the ones available to X onto ones that are available to Y, and if it's the other way around, we do the opposite. So the reason for doing this is perhaps not obvious, but it turns out to be useful in the analysis. And then we choose a colour uniformly at random, set the colour of X to the one we chose, and the colour in Y to the one that we mapped it to by the function f. So
Are we supposed to choose this bijection f once and for all for every pair ax, ay?
no, we do it every time. We
You choose it randomly, or you can choose it any way you like?
you look at the colourings as they are now.
No, but the bijection.
It's arbitrarily, isn't it? Because it's
Yeah.
And you can even,
Anyway.
but you can even choose the bijection depending on the current coloring of the rest of the graph?
Sure.
You think you'd want, you can?
Yeah.
Will that still preserve the right invariant measure?
Yeah, because all we're doing is choosing. This just chooses a random colour, okay?
Still a question.
Because it's a bijection. If it wasn't a bijection, you'd be in trouble, right? So this maximises the probability that they choose the same vertex and colour because of this bit, and this helps in other cases. So this analysis gives convergence in n log n time, and the big O does hide something about the maximum degree, but it's nothing too bad. And it will work provided this number of available colours, the maximum of the two. Did I define that? Maybe I didn't. Okay, so this is a bound on the number of available colours, a lower bound on the number of available colours in xt at u. So A alpha delta is a uniform bound at all times and for all vertices.
You mean with probability 1, not just in some expectation?
There's no randomness.
With high enough probability, that's all I mean. I mean that it swamps all the other things in the analysis. So when the number of colours is at least some beta multiple of the maximum degree, then clearly we always have this is at least q minus delta, which is what Eric said, so we'll always get beta minus 1 delta. So taking this alpha at least beta minus 1 is always valid, and that will just give beta at least 2, because that's what we require. So we get at least 2 delta colours, or bigger than 2 delta colours. And one thing to notice about the analysis is that it doesn't actually require that we start the thing from a proper colouring. We can start from any colouring. And the chain is such that it can only recolour things properly. So eventually, just by coupon collector, we will end up with a proper colouring. So this is a useful observation. So the analysis of this is, as Eric showed, it's easier using path coupling, but I'll explain eventually why we don't want to do that here. So, as Eric said, in the worst kind of case, we might have to use 2 delta colours, but to reduce this, we have to show that usually there is a bigger value of this, such that we can take this alpha bigger, and therefore it will give us a smaller number of colours. So the Q greater than delta was proved by Mark, Jerome, and also by Salas and Sokol by a different kind of analysis. Eric, as he told us, reduced this to 11 delta over 6 using a different Markov chain in a kind of careful path coupling. The paper that he mentioned that I had with Alan was attempting to use some kind of average case argument for triangle-free graphs, and it was based on this bound on the number of available colours, that a lower bound would be something like this. So that you would expect there to be more available colours if the graph's triangle-free than if it wasn't. So this is the kind of result we get. So if you assume Q and delta are large, then this comes to about beta e to the minus 1 over beta delta. So this will work as long as this is bigger than 1. So the number of available colours is at least the maximum degree, and this gives this 1.763, which just about beats the 11 over 6. So the problem, though, is that this doesn't recolour neighbours independently, and you have to handle some transmission of information of colours through the graph. So we could only do this by assuming that the graph had this very large maximum degree, about log n, and also very large girth, so that the information couldn't be transmitted fast enough. And then we could prove something sort of rigorously. So in the same paper, we observed that you could apply this to random graphs with densities which were about this kind of polylog n over n. They don't quite have the properties that we require, but they have them closely enough that the analysis can be pushed through. So Malloy immediately improved the result and showed that you could ignore some neighbours in this kind of path coupling setting which had both the colours of the vertex you chose, u in x and y in their neighbourhood, because they, if you look closely at the kind of analysis Eric gave, those don't actually contribute anything. They're good in both cases. So with this, he could push the thing down quite a lot to about 1.489. And the value of 1.489 is also the solution of this equation, which has a fairly simple probabilistic interpretation as well, but I don't have time to explain. So Hayes showed that the girth assumption was actually not required and was reduced successively to 6 to 5 and to 4 in some cases by Hayes and Vigoda. And there was a reduction to girth 5 for this number of colours by Malloy and Lau, but with a much larger degree. So then there was the sort of bigger breakthrough, which was the Hayes and Vigoda, who proved 1 plus epsilon delta and n log n mixing, but only for delta log n again. So this is very nice, but the analysis is quite complex, and this really is, is what you would like to prove in a more general case, but it can only be proved with those kind of degrees. For the lower degrees, we could prove with Alan, Tom Hayes, and Eric Vigoda some things which were close to the Malloy and the original Dyer and Fries, but with different values of the girth. So these are either 6 or 5. So a result of Fries and Vera, which is relevant to what I'll say when I get round to it, on locally sparse graphs gave the 1.763 for certain graphs with very large delta. And this locally sparse means there are not too many edges in the, the neighbourhood of a vertex. And there are also many things for classes of sparse graphs, so I won't really talk about those. So random graphs. So all these results, the Dyer, Fries, the Hayes one, etc., Hayes and Vigoda, can be applied to random graphs with the appropriate density. And you just do that by showing that a random graph has the required properties like degree, girth, etc. And random graphs of least low density tend to be fairly tree-like, so they satisfy the girth assumptions, though they're obviously not satisfied exactly. But what none of these things do is use the process which generated the random graph. They're more general, but they're indirect when applied to random graphs. But for larger P, random graphs don't have the kind of properties we're looking for, except for these Fries and Vera results, which would give the beta 1.763 for P up to little o1. So the only papers really that concentrated on random graphs was this paper we heard about this morning on very sparse random graphs, and this showed that if there was constant average degree, you could do log n colours. I've omitted the log n improvement, but we conjectured this result that a constant number of colours would do, and as we heard this morning, this was proved by Mossel and Sly by exploiting carefully this local tree-like structure of the random graph. But again, what this does is looks at the structure of the graph and then applies the algorithm. So what I'm going to describe is different completely, in that we will actually use the way the graph has been generated. So if we have larger densities, so they're bigger than log n, average degree, all the degrees will be roughly the same with high probability. So we might as well assume that they're all about the maximum degree. But the difficulty in analysing this is we can't use that the probability of the edge is p once we've determined whether it is an edge or not. So we can't look at it twice and say the probability that is an edge is p. So if we've looked, we'll say that this pair has been exposed. But we'll be able to compute in the random graph model if there are not many pairs have been exposed. So this is going to be the way that we do it. So we start the process by colouring independently at random. So this doesn't expose any pairs in the graph at all, but it doesn't give us a proper colouring, of course. But it does mean that each colour will appear roughly the right number of times. So we start the dynamics with this colouring. So it's kind of carefully chosen, but of course once we've proved it converges, it wouldn't really matter which one. So now we look at how many pairs we actually expose as we're doing this algorithm. So there's two ways that the things adjacent to u, pairs containing u, can be exposed. One is that you choose it with some colour, then at the worst you could have to expose all the pairs that have one of those colours at the other end, okay? So how many will there be? So the probability that I choose u is about 1 over n, and then I have to expose about n over q pairs. So I'll expose only about 1 over q pairs in expectation at each step. So, or if you like, p over q edges of the graph. So that's not many. The other case is that I choose a colour for some vertex v and it's my colour. Then I have to find out whether I'm a neighbour of that vertex. So what is the probability that I do that? Well, it's just 1 over q, okay? So, so with probability 1 over q, I expose one edge. And therefore, again, it's about 1 over q. So each step will expose about 2 over q, or 2 over beta n pairs, and about 2 over beta n edges adjacent to u, at least in expectation. And since we do this enough times, this is going to be true with high probability. So how many edges do we actually expose? Well, assuming that we can show this dynamics converges in n log n time, then we'll only expose about 2t over q edges adjacent to u, which is about log n over p. And this will be small provided that log n is small compared with np, which is exactly the regime that we're interested in here. So we learn also only a small fraction of the edges that are adjacent to u. So the dynamics finishes before we've inspected most of the graph. You know, seems quite surprising. But we just chug along and we finish before we actually know what the graph is. But the reason for this is simply that these colour sets are so small that we don't really have to do much checking at each step. So while it looks kind of surprising, when you think about it, it's not so surprising. So first analysis is to just use the kind of bound from the lemma with Alan, and we can recover quite easily the sort of 1.763 result for p equals little o1, which was previously shown by Fries and Vera. For p of order 1, then we can also do something similar, and using the same approach, these are the value of beta we get. So it starts out at 1.763, but it increases and it ends up at 2 fairly quickly. And you can improve it slightly by saying that some colours just don't appear at all in the graph, right? There's so many colours that some of them don't even appear. And if you do that, you get this improvement. But nonetheless, by the time you're up to about 0.7, you've hit 2. And you can't do better than the Jerome result. So we tried to improve this using Malloy's idea. But in order to do it, because we're using this direct coupling, we had to prove a direct coupling version of Malloy's path coupling condition. So it involves the number of neighbours of a vertex in one colouring which have a neighbour coloured with the other colour. So this is really just using a similar condition but applying the kind of counting argument that was in Jerome's paper. And it turns out that in order to do this, we have to estimate how many times a given colour will appear in one or other of the colourings. So we have to divide the analysis into 3 ranges of P, depending on how well concentrated this number of colours is. So the ranges are P little o 1 over log n. This is highly concentrated, everything works fine. We could have used path coupling here. But when P is bigger than 1 over log n, say, but still small, there is some concentration, but it's not enough to prove what we would like. And when you get P is of order 1, then it's not concentrated at all, and the analysis is much more complicated. So it was dealing with these 2 cases that required us to abandon path coupling, because the fact that there's no concentration means that you can't allow for the number of colourings along a path. So that would destroy the whole result. So we have to use this direct coupling, and then there are only 2 couplings to consider. So given a good bound on this, we can just complete all the calculations essentially in the random graph model. I mean, it may not look completely obvious that we can do that, but in fact it is. So we just need to analyse what this number of colours is. So we need some upper bound on the number of colours, and then the number of colours kind of more or less follows this random walk, which shows a fairly easy interpretation. So it will go up if we choose that colour and the vertex we've chosen has no neighbours that have that colour. And this is calculated in the random graph model. It will go down if we choose one of the colours that has that, one of the vertices that has that colour, and we decide to accept the colour. So that this needs us to have a bound, an upper bound on the number of available colours at any vertex, and then we would know that the number of available, the size of the colour set was at least this, and that's what we really want, a lower bound, so that we know there's plenty of things that have both these colours. So we just analyse this process in phases to get this bound. So with a better estimate of the size of these colour sets, you could repeat the original analysis that I gave before, and this was the best we could do before, you get this smooth curve going from 1.763 up to 2, and it can't be better than 2 here, because this says that the number of available colours has got to be at least a degree, and this is a complete graph at this point, so clearly can't do any better than that. So if we incorporate the Malloy improvement, then in the first regime we can get the Malloy bound 1.489. If we're in the second one, then we can get this 1.635, which is the solution of this rather awful looking equation. And this really just comes from analysing that process that I just showed you a moment ago. Finally, if in this range, the calculations are so horrible that we haven't done them yet, so I'll stop there.
Any questions? Okay, can we thank Martin again?